So we actually defined formally two objects, okay. So formally we defined two objects which were, so we went through lots of paths and finally we reached the notion of T decomposable graphs, okay, okay. So remember first I defined the notion of T decomposable graph, the first definition which we said for, okay, a graph G is T decomposable, a graph G is T decomposable if for all H subset of Vg, okay, there exists a balanced separator of there exists a balanced separator in graph induced on H. This was my first definition, if you recall, right? And we fixed this definition and we came up with another notion of T decomposable, right? Okay. So what we defined another notion of T decomposable. My God, why I will die. And what did we say? A graph G is T decomposable. Okay, if for all H subset of Vg, for all W subset of Vh, there exists a W balanced separator. I think separator is E or A? Separator A. Are you sure it's E or A? Okay, very good. Okay, let's write it in a way that it can go for anything. Okay, okay, fine. There exists a W balanced separator S in H, which basically means like you have here H, you will find your S, right? And then if you look at the connected components, then for any Ci, Ci intersection W is at most W by 2. Okay, so this was a balance separator, and then from here we got the notion of, so for we use this, what did we show? Then we showed a theorem which said if a graph G is T decomposable, then it has a good decomposition, of width, what was it? 3t plus 4. And this good be separated out, and that was precisely the notion of tree decomposition that we were looking for. Okay, so what was that? So we said that let G be a graph, okay, and what was this? We had TR and F be a decomposition such that what happened? Such that we had three property. First property was that if I look at union S in VTR, f of S, this is equal to Vg. Like, secondly we said for every edge u comma v, there exists S in Vt such that u comma v is a subset of f of S. Like, so there is a bag which can, and this f of S, this association of, so remember this function is how from VTR to 2 to the power Vg, okay. Since it's a subset of vertices, we call it a bag, okay. And third, what did we show? That this guy also had a property of certain beautiful connectivity property, which was that for every V in Vg, okay, we defined the notion of LV, which was like S, okay, LV equal to S, S in VTR, and V is in f of S, okay. Then LV is a subtree of TV. These are the three properties. And what did we show here? And we actually showed two theorems. So if a graph G is T decomposable, then it has a tree decomposition, right? This is what he said, tree decomposition of width 3T plus 4. And we also proved a partial convert. If a graph G is T decomposable, then it has. So what is the partial converse we proved? So we showed that if a graph G has tree width T, then it is T decomposable. Then it is T plus 1 decomposable, right? Right? We proved this. Okay. And how did we define the notion of width? Notion of width was maximum over S in V of TR F of S minus 1. So this was the notion. And tree width of a graph was to find a tree decomposition with minimum width. Okay, fine. So the reason why I wrote this, because we were able to use this for a proof, right? And it just happened that when we were trying to meet all the requirements, but it was a good old open question whether this definition is enough to prove something of this nature. That is, if a graph G is T decomposable with respect to this definition, okay, then it has a tree decomposition of some width. Okay, it was only settled in 2016. I think it's a JCTB paper, which has not even yet appeared in 2019, which shows that even with this T decomposable definition, we can show it is 105, tree width of G is at most 105 times T. Okay. If it had been a graph theory course, I would have given a proof to that, because this is one of my favorite things which I have tried proving for a long time in my life. Okay. Unknowingly. Not that I knew that this is an open problem or something.
This theorem would prove that it is T decomposable
with respect to this definition, right? Here think of this way, it's like a weighted version. Here it is an unweighted version. Unweighted version also implies that tree width is not too large, right? It still is a linear relation actually, right? But this requires like 10-page proof, okay? Okay. So this is why I told you, so that I could have built my whole theory starting from here, but that would have required me to give you a proof which is extremely difficult, and then it would have hindered us in developing other things further, okay? So this was, like to do in the first half of my lecture is to give you some simple properties of, like structural properties which has nothing to do with algorithm, what these tree widths are, what is this graph of bounded tree width look like, and what kind of properties do they have. And towards that I first introduced the notion of simple tree decomposition, if you recall correctly yesterday, right? But we didn't prove why simple tree decomposition exists first of all. Okay, so these are little trick. So we are in the next lecture we'll try to get algorithmically, okay, the algorithmic property. Okay, so we saw an existential proof for this, existential, right? It was not an algorithmic proof. Okay, so we will spend a lot of time making this theorem constructive. Okay, so we will take the same ideas and try to make them constructive, see what are the obstacles are and how we can tackle those obstacles to make the algorithm constructive. Okay, so in parameterized complexity, a lot of times we come up with existential theorems and we try to make it constructive. For example, if you look at the paper which you presented for your CREATE seminar, it has a couple of such objects, but it is really it takes a lot of efforts to make it algorithmic. Another example is, so if you heard of this called Lova's local lemma, okay, which talks about some intersection of sets and all, and if some property happens then you can satisfy that many clauses of a formula, right, like K-SAT formula. And it took lots and lots of efforts from people to make that lemma constructive and come up with an assignments which really satisfies. So it basically tells you that if this probability is there, then every K-SAT formula has at least that many satisfiable clauses or something. Okay, but how do you make it constructive? Okay, so you need lots of efforts. Similarly, Lova has proved that For linear matrix, rep sets exist and its subsize P plus Q choose P. Now, how do you make it constructive? It requires completely different set of tools and tricks to make them constructive, okay? And of course, on the way you might lose something. So we'll see one of such things today. Okay, but I define the notion of simple tree decomposition, if I recall correctly. So what is the notion of simple tree decomposition? Okay, definition. Okay, a tree decomposition Tr comma F, a tree decomposition Tr comma F is called simple if what happens? If for any two nodes T1, T2, f of T1 is not completely contained inside f of T2, and similarly f of T2 is not properly contained inside f of T1. Then I am going to call this a simple tree decomposition. Okay. So the lemma I want to first prove, okay, that let G be a graph such that tree width of G is at most T, then there exists a simple decomposition, simple tree decomposition of width at most T. So like I will not going to lose anything because I am going to work with a simple tree decomposition. Okay, how do we prove this? Did you think about it? Did you not get it? Got it? It's obvious, right? So suppose here is my tree. Okay, for now let's see you have some T1, T2, say they are edge, T1, T2 is an edge for a change. Here is a T1, here is a T2, okay, and suppose f of T1 is a subset of f of T2, or say f of T2 is a subset of f of T1. What can I do? What happens if I just contract this edge, right? I just contract this, I move this here, right? So I keep everything same, I take T1 here, right? And I add this node, let's call this T2 here, I move this T2 here, and then I have like this, right? So T2 was completely contained inside T1, right? T2 was completely contained inside T1, nothing would change, right? Every vertex is still contained inside everybody, right? Because T1 was f of T2 was a subset of f of T1. So if a vertex which is present here is also present here, every edge is present, still present everywhere. Things were connected, they are connected even now, so nothing changed. Otherwise they are not this, then fine, there is a unique path say T1 here, T2 here, right? Look at this unique path, okay? Look at this unique path, look at this unique path, okay? Okay, look at this unique path. What we know, suppose for now again I know that suppose f of T1 is subset of f of T2. This is what it is. Now what does connectivity implies? A vertex which is here and which is present here, it is also present on all these vertices, because otherwise connectivity property will be, the third property will be violated. Which implies, so suppose this is like, let's just write out T1, T2 prime, T3 prime, T4 prime, dot dot dot, TQ prime, and then T2. So what do I know here? I know f of T1 is contained inside, is a subset of f of T2, f of T1 is a subset of f of T2. Do I know anything more? This one is completely contained inside this. What does that imply? This guy is a subset of every bag. Okay? So now I try to contract first T1 to T2 prime. I contract, same operation, right? I did. Nothing would change. Okay? If f of T2 prime is contained inside f of T2 prime, I will again do the same thing. If not, then I am done. So just keep doing this. This is a finite number of steps by induction you can prove. Okay? So basically what does it implies? That given a tree decomposition which may not be simple, I can come up with a tree decomposition which is simple. Okay, excellent. But I also wrote something else. And what did I wrote? So first, then we wrote, then there is a simple tree decomposition of width at most T, and now let's add, and vertex set size of TR is at most a vertex set of G. How do we prove this? Okay. So here is a way to prove this statement. Okay. This is my workspace, okay, and this is my log space. This is my workspace, which is log space, and this is like what's it called? Output tape. So I output here and I work here. Nobody understands jokes in this lecture. So we can rub this, no? Okay. So now you have a tree. Suppose this is R, rooted. Now for every vertex in VG, I am going to do something. For every vertex V in VG, I am going to do something. Look at all the nodes, or look at LV. What is LV? S in VTR, V is in FFS. Right, this is what it says, right? Okay. Now among LV, pick SV where whose distance from root is minimum. Root is minimum. Okay, and this is unique because I cannot have two. Look, so look at this is rooted, subtree rooted. This is a subtree. So look at the guy in this subtree which is closest to the root, right? I cannot have two things which is closest to this. Otherwise, it will not be connected property. So this is what I associate with. So I have given you a map. I have given you a function from vertex set. So this is a function from vertex set G to vertex set TR, and it is a function, right? Two things can go and try. Now I am going to claim, which is cute, if TR comma F is simple, then F is surjective. Oh, I shouldn't write F, let's write G. Then G is surjective. Then are we done? What is the meaning of surjective? For every guy I have some vertex which is mapped to, right? So every guy, and look, this is unique. So every place you might have some set of objects which are mapped to, right? So if I show this is a function is surjective, I am done. First, why R is surjective? All I need to show someone has mapped here. First of all, if R, nobody has picked up at R, my G doesn't map anything to R, it means I claim f of R is empty, because if it had anything non-empty, then all those vertices will be mapped to the root, right? But empty set is contained inside everybody, right? So this condition would be violated, right, of simplicity. So clearly someone is mapped here, okay. Now let's look at some guy who, suppose here nothing has been mapped. What is the meaning of nothing has been mapped? It means it has some set associated, right? Let's call it S, let's call it S star, which is his parent, because it's not root, then everybody has a non-trivial parent, okay. Look at S and S star, nobody has been mapped to S. It means, look at any vertex here, he also occurs in S star or ever, because it's connected set. So and I did not mark S. Imply that f of S is a subset of f of S star. That's a simple, that's contradiction to simplicity, and we are done. Okay. So we prove this, right, and we saw certain corollaries out of this. This implies, what is this corollary? Number of edges in a graph of tree with at most t is at most Tn. Degeneracy of G is at most T, it is T plus 1 colorable. This is what we show, okay. So let's prove some more structural properties of these guys, okay. Question? Okay. So okay. So we do not need any more definition of T decomposable, this and this. We also do not need any of these things, okay. So let's rub this portion, okay. I will keep this definition for you to sometime still digest it, okay. Why should I rub this? I can use this for all good purposes. Such a nice drawing. Okay. So the lemma or theorem which I want to prove is the following, okay. This is a lemma that tells you how good separation property it is. Let T1, T2 be an edge, S1, S2 be an edge of some TR, okay, and let T1 and T2 be the tree, T1, T2 be the tree of TR that contains S1 and S2 respectively. Then what is the condition? Then f of S1 intersection f of S2 separates, okay, separates U1, which is union T in VT1, S in VT1 f of s and u2 equal to union s prime in Vt to f of s prime. Okay. So let us go back to the picture. What is it tells us? It is telling us pick up any edge. So if I pick up say this edge, I pick up this edge, for example, say this is S1 and this is S2. Now if I delete this edge S1 and S2, I get two trees. Okay, if I delete this edge, I get exactly two trees, right? If you delete any edge, okay, I am going to call this is T1 because it contains S1, and let's draw more here, okay, and this tree here is T2. And what does this tells us? Then f of S1 intersection f of S2, and what is U1? U1 is union of vertices appearing in the backs here, this is U2, and U1 is the vertices in the backs that appears this one, okay. So what this tells us that look at all the vertices, look at, or basically I have to show that to you, look at G minus f of S1 intersection f of S2, which is same as U minus, say call this W. So U1 minus W is here, U2 minus W is here, and there is no edge here, this is not there. This is all that we have to project, like separates, meaning after I delete this object, then from here to here I cannot go, which means there is no edge between here and here. Suppose let us pick up this vertex, say U and V, and suppose there was an edge. Look at this U and V. So there is a bag S which contains both U and V by the property of tree decomposition. For every S there exists a bag, okay, fine. So if U and V is there, then there is a bag which contains S. So where that S be? Can S be here in T2? Why? Because we know V is here, because, and if edge UV is here, then V by connectivity property should also be here, right, because this bag contains this, right, because then if there is a bag S which contains U and V, because there is an edge which contains, and I know V appears somewhere here. Now what I know, that all the bags that V is contained in is connected, right. So if V is definitely here, V is definitely somewhere here, then it is on every path, so they are in the intersection, right. And similarly we can argue for that S, this containing S cannot be here containing UV, because then I will look at U and do the same argument again, okay. So what does it mean? This is exactly what is like tree like structure property we have been looking for, right. This is exactly why we call this, oh, tree decomposition is tree like, because if you look at any tree, delete an edge, there is no edge from here to here. So now I delete an edge, right, and I delete what? The common set of vertices between both of them which I am passing through, then they behave exactly like a tree. There is a complete separation, okay, okay. Here is another lemma which at least I find them very useful, okay. Here is a lemma. Given a set W, given a set W subset of Vg, okay, there is either there is either S in TV such that W is subset of f of s. So, given a set W of my graph, either I can find a bag which contains whole of W, okay, whole of W, or there exist vertices, W1, W2 in W and an edge S1, S2, edge S1, S2 in TR such that something interesting happens. Okay, such that W1, W2 lies outside f of S1 intersection f of S2 and they are separated by in G. So, what is it meaning? What does it tells us? So, let us draw this picture. Okay. Okay. Okay, these two lemma are from Diestel, edition 3. What is this lemma called? 12.3.1 and 12.3.4. Okay, let's stop this. I think I can draw another tree. Okay, so what it tells us? Okay, before I forget, this is not for you. Next, obstruction. I'm not fully prepared, so I have to. Okay, so what does this lemma tells us? It tells us you give me a W, you choose your any set W. Then either I will find you some S here such that W is subset of f of s. This could happen. Great. Suppose if this is either this is true or what else could be true? I will find you an edge, say S1 here, S2 here. Okay, I will find you an edge S1, S2. I also will find you some W1, W2 inside W such that you look at your U1 the way we defined U1 before here. Okay, look at U1, look at U2 and look at U1 minus f of S1 intersection f of S2 and look at U2 minus f of S1 intersection f of S2. Look at these two things. W1 is here, W2 is here. It means either I can put you inside or there is an or W gets separated, right, by some edge. This is all that it is saying. If you look at this easily, all it tells me is that either W is completely contained inside some set or it is separated by some edge. Like so, and what is that separation? F of S1 intersection F of S2 is that separation for W because W is not contained inside left, W is not contained inside right. Okay. Good. How do we prove this? And the reason why I am presenting this proof to you because the proof technique is very cool and hopefully you will be able to find. Okay. So this is called orientation trick. Okay, this is called orientation trick. let's pick up an edge, pick up any edge. Okay, so I picked up this edge, I delete, so suppose this is like S star, S double star, delete F star, F intersection F double star. What will happen? Either this, if I delete all this, then in this part I have some W1 or some W2. Happy, no problem. Then I have found the edge which is required, right? I have found a pair W1, W2, and I have found an edge whose intersection, if I delete, W gets separated. Otherwise, what happens? W is either fully contained inside this side or fully contained inside this side. So if W is fully contained inside this side, orient this edge, orientation trick. This is why you orient this trick, orient this arc in this direction. What is the meaning? Which just tells us that after I delete this, my whole of W is neither in the intersection and it is completely contained inside this side. This is exactly what it means. Okay, fine. So you orient all the edges. So like either you will find a separation or you will keep orienting, right? Keep orienting, keep orienting, keep orienting. Idiotic. What is this? This is a forest, right? This is a tree, right? So any orientation of this tree is a dag. So there is a sink. Okay, either I succeeded or we will find a sink. What is the meaning of this? It tells us all of W is contained inside, after I delete this edge, this side. This edge tells me it is contained inside this, which basically means it is contained inside here. So if this is S, this implies W is subset of Fs. That's it. So this is what is called orientation trick. So I have oriented in a way that if I look at source and sink, I am able to gather some information about it. Why did everybody just point him to? Everybody pointed him because W is completely contained inside this. Okay, there are many other proof. Okay, but I like this proof, so I told you this proof. Okay, and this, I mean, you will be able to use many times. In what situation? Now look at our yesterday's proof for vertex separator, right? Oh, orient the edge towards the heavier side, right? That's it. So either I find this vertex separator or I orient towards the heavier. What is the source? Source is your vertex separator. That's it. So like you can apply this trick for whenever you want to go towards something particular and you are working with tree, forest, so you can orient it this way that you can get a source or sink. Or in any case, if you can get a dag out of this in some way, you can argue, then also you can argue some of these things. Okay, good. So what is a corollary of this? Let me write a corollary of this. Okay. Okay. So another lemma, which is let me not write a lemma. Let me call it corollary because it is a corollary of this lemma. I have not even told you. We are just still talking in completely abstraction. Any click, okay, any click of G is contained inside a bag. So if your graph G has a click K, it is contained inside some bag. Why? I mean, how, look, I wrote corollary of this. Either S in TB such that this happens, or, so suppose if this happens, what happens? It's a click. How can you find, if it's a click, I find some intersection and I find here and here, then there is an edge. So it's really a, okay, good. Now you will understand why I wrote the word obstructions. okay. I don't need these things, so I rub these things, okay. Let's use the word obstruction. What is obstruction? I will say H is an obstruction of H is an obstruction to tree width G if H is a minor of G, then tree width of G is at least tree width of H. Look, this is anyway true, okay. So what is new I am talking? I said H is an obstruction of tree width G if H is a minor of G, okay. Then first is this, and we have some form of lower bound on tree width of H, okay. Then I will say, look, and suppose, okay, so let me write down tree width of H is X, okay. Then I say H is obstruction to G having tree width X if H is a minor of G, that is it. So suppose tree width of H is X, some H, I say H is an obstruction to tree width G having value X if H is a minor of G, right. And this is definitely true, right, because we know that tree width of G is at least tree width of H, right, and since H is a minor of G for which is this, so tree width of G is at least X. So if I can show that I know then I can say that, oh, you cannot show tree width is small because this guy is present there, right. So can you give me a lower bound on tree width of G in terms of click size, in terms of click? What? So tree width of G is at least omega of G, where this is maximum size of click, right? Great. So this is a lower bound.
I didn't understand. So H is an obstruction, then H is a minor, or if H is a minor?
No, tree width of, I said H is an obstruction to tree width G having a value X if H is a minor of G. Otherwise H is not. If H is not itself a minor, then I cannot conclude from here. That's it. So I said, okay, let's try to do maximum size of a click, right? So suppose, can I say, so I know we just now learned the tree width of G, why? Because if you have a click, then it must be in some bag because of this corollary, right? Which implies that omega of G. Can I say this is function of click of G, upper bounded by this? I say, look, if a graph does not have a click of size 10, then its tree width is like some function of 10. Can I say this? It would be great, no? I mean, if we could say this, right? We will pause. So, I have a tree. Give me a tree decomposition. Now, let us make our hand dirty, right? I mean, we did lots of abstractness and blah blah blah. Now, let us make our hand dirty to just understand more things. Do you know how to make a tree decomposition of a tree? Okay. Or cycle of length Cn. देखो नंबर बोलने से ना काम चलेगा, आपको देना पड़ेगा एक एक्सप्लिसिट डिकम्पोजिशन, तब नंबर बोलिए, तो तब तो फिर मेमोरी हो गया ना, वो नहीं चाहिए. Definition, we have a definition, we should be able to construct it, right? And then we say, hey, look, here I constructed and hence it is this. Otherwise, I mean, what's the point? You are talking about cycle, okay? Not for the trees, right? Okay, fine, fine, it's okay. I can live with it. 2, 3, 4, okay, up to n. So what will I do?
Put a back with vertices n1, 2, then back with repeat in all the vertices of the tree decomposition, repeat n, and then put 1, 2, then 2, 3, then 3, 4, just like that.
So what is my, so look, you have to give me two things, right? So give me a decomposition, you have to give me a tree rooted at something and a function f. So what is your TR?
Make a path.
Okay, I made a path of length.
I'll tell you.
Okay.
First vertex.
Okay, let's call it S1, S2, SL. Tell me what is f of S1.
N1, 2.
N1, 2. Okay. Okay. So and what is f of Si?
N I plus 1.
N I plus 1. Why not 2? This is our tree decomposition. All of you agree? Is it connected? Okay, excellent. Give me a proof, no? I mean, like, it won't be is not enough for me, no? Can you give me a proof that this is an optimal tree decomposition? I cannot get a tree decomposition of width 1. Why? Width 1 means every bag has size 2. This is a tree decomposition of width 2 because every bag has size 3. I agree. But why can't you give me a tree decomposition of width 1? That's a question, no? I should be able to prove it, right? I mean, you cannot be able to do this, that's not an answer, right? We have to be mathematically prove it, hey, if this happens, then this can go wrong or this can go right. You get my point? I told you, right? So then I have a reason to believe this is optimal, right? Not because you said, because triangle is a minor of Cn. That's it. So
Separated is like intersection of
no. So I didn't get what you're saying.
in order to separate a cycle you need delete at least two edges.
Two vertices. Yeah. So two edges.
Sorry,
Yeah, you at least need two edges as well as two vertices. Fine.
and we gave a separated with intersection, right? So there has to be size at least two,
Yes.
and that gives you a
Lower bound of
lower bound on three.
two or one, because back side only is two. Because f of s1 intersection f of s2 could be some f of s1 for all that I know. So like a lot of things. Okay, so you are so smart people. You know how to find a tree decomposition of a cycle and prove it is optimal. Trees. First, give me a tree decomposition, no, madam? You have to give me a tree decomposition which is like TR, comma F. Look, I am just going by definition. I am not trying to do anything. I am just saying, here is a definition. Please give me an object which is like this. Give me an object which is like this. Ryan, tu hi bol de yaar. At least I will feel better. Someone in the class told me. Or Ashwin, you can also tell me. At least I will be happier rather than me telling. Tell.
So you root the tree with some root.
So we just take the T as TR with some vertex rooted. Okay. So let's call TR where T is rooted at some vertex. Okay. Some vertex, say R. Right. So we have rooted this guy. Okay. So now I have this tree which is exactly T. Okay. Now he will tell us. So this is TR, which he has formed with the help of T. Okay. Now we have to give F.
So for each node you add the node and its parent.
Okay. So for every S here, for every S, it is S and parent of S. Am I right? Okay. Except what should I do to root? The guy has no parent, no?
Just
So for now, let's keep it just R. Clearly, every vertex is there. Is it connected? Are you sure connected? No, I mean tree, this tree is connected, but for every vertex, all the objects in which it appears should be a connected subtree. No? So every vertex appears where? In how many places? At most one. You took this guy, no, yeah, he appears in himself and this. So twice, and that's an edge. Good. So clearly, this is good. No, I'm very happy, extremely happy. So this is okay. Okay. So this is why tree width of tree is 1, not 2. And you can also prove for yourself. G has tree width 1 if and only if G is a forest. Tree width at most 1 if and only if G is a forest. Okay, it's characterization. It's not that. Okay. Excellent. If a graph G has if a graph G has vertex cover K, then tree width of by the way, I forgot to tell, okay, if TR is path, it is called path width, okay, special case. Less than equal to? Why?
And the edges coming out.
Okay, so this is a vertex cover. So what should I do?
You just make the edges one back. And
Edge one bag.
the edges. So each edge has to be contained in the back.
What is your TR? Okay, let's go with the definition. What is your TR?
TR should be rooted at vertex cover.
There is no question of rooted. TR is your tree. You have to give me a mapping from F which tells me which is associated at which place.
All contain the vertex cover.
Hmm?
Root contain vertex cover.
What is my tree? Suppose I have V1, V2, VQ, okay. So suppose I take a path, okay, and I call it S1, S2, SQ, okay. At SI, I map vertex cover plus VI, okay. Is this a tree decomposition? Valid, every vertex is there, every edge is there, and every other vertex Vi only appears here, so that's perfectly fine, and every other vertex of vertex cover appears in the whole thing, so this is fine. Okay, so this is what I mean, that you have to give me TR and this. Then what? Then tree width of G is
S1 is they have an edge, right?
S1, this is my tree. My function of S1 is what I am going to map to function of S1, vertex cover union V1. Okay. So what is the tree width of G then?
Take the 3D composition of the remaining graph and add feedback vertices.
Excellent, excellent. So this is like basically K plus 2, right?
K plus 1
That is one.
minus 1 and K
All right. Right. So what he said, look at this forest, take a 3D composition of this, add F to every bag. That's it. Done. Okay, excellent. I never knew that my class is so smart. But your smartness ends now. Tick, 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 What's the tree decomposition of this? Maybe it's too big, no? Can you make a tree decomposition for this? No memory again, please. Bana, draw. There's a reason I'm drawing those things. I mean, like, I give you a lot of time to think, because I know you people have not been taught tree width before, so spend some time thinking. What is your guess? Okay, let's make life easier. What about this? It definitely contains triangle as a minor because I have a cycle. So tree width of say 2 cross 1, 2, 3, 4, 5, 6, 2 cross 6 grid. I don't know what it means. Okay, there are 2 lines and there are 6 lines. This is what it means by 2 cross 6 grid. I mean, I don't know. So clearly, let's say grid 2 times 6, tree width of grid 2 cross 6 is at least 2 because it contains this. How? I can delete all this and then contract this, so I will get a triangle because triangle is a minor of this graph. So this is clear. How else? Maybe we should make.
Wait, how are you defining this function?
I am not didn't define anything. All I said to you, the tree width of this graph is at least 2.
It's less than equal to 6
Why it is less than equal to 6?
because vertex cover less than equal to 7 because this requires 6.
Okay. So C says that. Okay. Let's call this G. Okay. So what you say tree width of G is 7. How 6? Vertex cover is 6. Are you sure? Is the vertex cover 6? 1, 2, 3, 4, 5, 6. Impossible that you can get a vertex cover of 6. You cannot. I don't think you can draw. 6 is okay? Why? 7, right?
No, 6 because you just pick alternate from each matching. So like you take in each matching, pick alternate.
I had a better region. It's a bipartite graph, so maximum matching is equal to minimum vertex cover. So this is 6. I don't have to do this alternate region. I mean, valid region, no? So correct 6. It means the bag size will be 7. No, 1, 2, 3, 4, 5, 6. It is a perfect matching. So why will you have? There are only 12 vertices. Please, guys. Okay, I mean. Okay, let me show you how smart we could be. Maybe we could take this and then I could take this. Okay. Do you see something? Okay, so now this is left So what should I do? I take these three. Now I will take, what should I do now? I can do many things. I take this. If you notice, I always take 2 common from the previous one. So I am just trying to follow my pattern. Now what will I do? I take this. I mean, up to me how I make it. Maybe I have huh? I have done something wrong, no? Okay. So otherwise it is redundant. I could have added again another one, which is redundant. You are right. So I should just take this. Keep doing this, right? It's also tree decomposition. Actually, it's a path decomposition, where like my path will be like this, this, and its tree decomposition is 2. So this is actually equal. Great for us. No? Okay. Okay. Now, still I can say that tree width is at least 2. Next, what should I do? Huh? My choice, no? I said at least 2. Maybe you can make a decomposition of width 2 for myself. Okay, let's see. This girl is making me crazy, so no, okay for my. What is the maximum size of a planar graph? Of a planar graph? Maximum click size of a planar graph? 4. Very good. Just remember. Is independent set polynomial time solvable in planar graph? I think it is, no? Independent set you can solve in polynomial time on planar graph. Nothing. I am just doing my tree decomposition. So now I should maybe make intersect at 3 places. No? So how should I go about it? I will take this one. Why?
Because you have to replace this vertex because there is an edge. If you are taking
Wait, no. What you have to repeat?
this is next bag and there are 2 vertices in like there are 2 vertices, one vertex in here and one vertex in here, which has an edge.
So I all have to make sure that there is a bag which contains this edge. Am I not that? I have not drawn.
She's saying that the last one is the second column. The 2 that has a
This and this. I know. I have not drawn my tree decomposition yet. No. No. What is your tree decomposition property tells you? For every edge there is something such that this happens. That's all that it says.
this is not your second bag. This is just a bag.
This is my second bag. Why second bag has to contain an edge from there?
Because then connectivity won't be there.
Have patience. Maybe. I mean, I don't know. Maybe I'm just making mistake for all that I know. Okay, so this is what I will do. Okay, okay, and I want to repeat this. What will I do next? I do a blue one. Let's see what happens. Maybe I'm just wrong for all that I care. This is my next bag. Okay, did I cover whatever I wanted? For whom? Why? Which vertex is not there? Let's just zoom in. Which vertex is not there? Up until now, if my, say, start with blue bag, okay, blue, green, red, blue, green, red. Tell me which vertex violates up until now. Suppose this is what I did.
The third property, the connectivity.
So for which vertex?
So second row, let's say.
This vertex?
Second column, third row. So
This vertex?
yeah. So this vertex was there in first bag.
This vertex was in the first bag.
Not there in second bag. It is not there in third bag. It is again there in fourth bag.
Okay, good. That's a point. So what should we do? So this is not correct. She's right. Okay, see? I'm just playing around. I'm not trying to actually make a 3D composition. This much I know how to make 3D composition. Don't worry. Okay. So what should I do? I'm making a path decomposition. I'm not making a 3D composition. So you said, okay, this is fine. Next, what should I do?
We can skip third vertex now.
This vertex.
First column, third vertex. We can skip that because it has been satisfied.
Okay.
Let's take two vertices from here and two vertices from here.
So
First two vertices from first column and last two vertices from second.
you mean this?
No, like first two from first column.
So you mean this,
And second two from last two from second.
like this. Okay. Next, what should I do?
Now first vertex and all three of the second.
First vertex.
First vertex of first column and all three of second.
Excellent. Proud of you. You mean this?
Now we can repeat this.
Repeat this. Very good. Right? But what is the tree width of this? Right? At least the way we have drawn. Maybe it is 2. Okay? So you found the pattern. Okay? So does it matter if I drew 2 or 3 or 4? Okay, so let's draw a slightly more bigger example. Look, there is some reason I am like zooming into this grid and trying to draw. Okay? I mean, I am not very much enjoying doing this, but I thought all the time I talk abstract, sometimes let's make our hands dirty so that you learn. So suppose this is my grid. What is the dimension of this grid? 1, 2, 3, 4, 5 times 1, 2, 3, 4, 5, 6. 5 times 6. Okay. So there is some pattern emerging. So now what will I do? Again, as you said, let's do this. Then what did you do? You forgot this guy, right? If I recall correctly, you did this? No? Isn't this what you did? Okay, sorry. Okay, we should skip this one. Sorry. Okay, so let's do like this. This is what you meant? Okay, excellent. And next, what should I do? I should go here, right? Right? Am I right? And then we should do this, right? And then we should do, okay, too much of, right? Like this. And I can repeating this, right? Now I take this and proceed like this. It's a path decomposition. But its width is how much? Huh? 4. Or 5. 1, 2, 3, 4, 5, 6. So it's fine. 5. How do I show that this is lower bound?
At least for the previous case, we can show that the click of size 4 is there.
It cannot be. A click of size 4. Okay, maybe.
Minor.
Okay, so it's 4. The reason what I'm trying to tell you, these are planar graphs. They have no click. And if I can show that if I take some m cross n grid, then its tree width is at least min of m comma n, because this is what is happening if you notice. Right? I mean, I could have, look, you could have done this if you'd have thin grid, like then you could have just done the other way around. So basically, so tree width of, let's say, grid of m cross n grid, it looks like that something of this nature should be true. Okay, and if I can show this to you, what does it imply? That grids are present in planar graphs. So all these grids are planar graphs. So planar graphs cannot have a bounded tree width, right? It has to have an unbounded tree width, because as I take a big and big grid, they all are planar graphs. But it also implies that this conjecture is false, that I cannot bound my upper bound of, so click is not a canonical obstruction, but maybe grid is, who knows. Okay, so let's show how to prove this. Okay, okay, I should not be teaching all this, but let's see. I was supposed to teach you algorithms, but I'm teaching you graph theory. No reason why. Okay, do remember these things. Okay, I'm going to introduce a notion of brambles. Have you heard this word called brambles? Any one of you, have you heard this word called brambles? Okay. Now does it look like that we have reached some crescendo in the course? Right? So what are brambles? Okay. Okay. Let G be a graph. Okay. Let G be a graph. Okay. Let G be a graph, and S and T be two vertex subsets. Two vertex subsets. Okay. We say that S and T touch if first, if either S intersection T is non-empty, is not equal to empty, means they have some common vertex, then I say they touch, or there exists a vertex S in S and T in T such that S comma T is in the edge of my graph. So here is a set. So if they intersect, I call them they touch. Suppose they do not intersect, but they have an edge between them, then I call them that they touch. Okay. A set of mutually touching connected vertex sets of G is called a Bramble. What does this say? A set of mutual, so this is a family of vertex subsets of my graph, okay. It is a family of vertex subsets of my graph, and what is the property? First of all, they all are connected set. They are connected set, okay, that is the first thing. And you take any two of them pairwise, they touch. So either they have a vertex in common or there is an edge between these two vertexes, okay. So this is what is called a Bramble, okay. I am still keeping this definition so that hopefully it will skim through your head, okay. And so a set of mutually touching connected vertex sets of G is called a Bramble, okay. And now there is a notion of order of a Bramble. What is order of a Bramble? Is minimum hitting set of F. So look, these are, I can think of this as a universe being vertex set of G, and these are family of sets, and minimum hitting set, like set of vertices which intersects all this, like think of them as universe and family of sets. So this is basically a subset of vertices which intersects all of these people. This is what is called order of a Bramble, or I call it minimum hitting set of size of minimum hitting set, okay, not a size of a minimum hitting set of F. And what is a theorem? 1993, not going to prove. If it would have been graph theory class, I would have proved it, because this I have proved in 2010, long back, okay. So here is a theorem. Remember this, okay, even if you do not know the proof, remember this. Let k be greater than or equal to 0 be an integer, okay. Then, okay, a graph G has tree width k, okay, tree width greater than equal to k, if and only if, okay, if and only if it contains a Bramble of order k, Bramble of order strictly k, okay. So it is a characterization in that sense, right. So if I show you that I have a graph G and I want to find a lower bound on my tree width, if I can show you a Bramble of order strictly more than k, it will imply the tree width is greater or equal to k, okay. Okay, so that is the last thing I am going to do now. Let us take, first let us take n cross n grid, okay, and let us show a big Bramble, okay. So I have n times n grid, okay. So here is my F. What is going to be my F? My F is going to be, okay, Cij, I between 1 to n, j between 1 to n, okay. So what is Cij? So what is C11? Means these vertices and these guys, I take this, okay. So this guy consists of this. What is C12? It will consist of this. What is C23? For like C13, third line, and so on and so forth. So basically this, then this and this, this and this, are they pairwise intersecting? You look at any two guys, right? One, you look at any two guys, you are going to pick up whole of one line, you are going to pick up this. Look at any other I prime j prime, right? Any other I prime j prime, you are going to pick up this and you are going to pick up this. So of course they mutually intersect each other. So this is definitely a Bramble. And what is its order? Order is a minimum hitting set. Look, whatever happens from here, right? Otherwise how will, okay, so if you pick something from here, you have to pick, but okay, so whatever you pick, let's just delete that row and column, okay. Look, so this entry, so look at any minimum hitting set, so look at from Cij, you will hit something, right? Let's delete that entry. By deleting that, let's delete the corresponding column and let's delete the corresponding row, okay, but you still have this crosses, okay. So you, for the next one also you will do, so anytime you are going to drop, you are going to drop one row and one column at a time, right? So minimum hitting set will be at least, for f is at least going to be n, okay. Did you get the point? Look, you will pick up something, no? So just decide which one do you want to pick. For any minimum hitting set, we'll pick up something from this set, right? So I decide to pick this. Let's delete this, like this cross, I will delete it, right? So when I say delete it, I mean whichever object which are being hit here, you just delete it. So which object will be hit? All those objects will be hit which contains this guy, right? Which is what? Think about it. What is this? Like this, like this, like this, like this, like this, and like this. These are the only people, only those crosses will be hit by picking this, right? So you delete all this. You delete all these crosses, right? So every selection, okay, or maybe you decided to pick something here, then which will hit, which will reduce, then it will reduce all those guys which is this and this. So you pick up a vertex, either you will get rid of some C, so if you pick up a vertex here, look at the first column, okay, and first row, you have to pick up someone. So if you pick up something here, like say you picked up C1, like first row, and jth object, if you picked up this, right, suppose you picked up alpha ij, this vertex, it means not ij, 1j, then you can take care of, this guy can take care of which one? All those Cij where you have the first row, so you throw them out. If you would have picked up alpha, say alpha I1, first column, then all those guys which has 1 in the second thing you can hit. So by picking the first vertex, either you get rid of one family of crosses or other family of crosses, but it can only take care of one family of crosses, which basically means from every row and column, like fix up each row and column, you have to pick at least one vertex, which if you argue yourself, you can show that it is at least n, this is why I took n cross n, right. So if you had min of m comma n, you can always prove that m is needed, okay. So what did we show? This is a Bramble of order n. So this is a Bramble of order strictly n minus 1. If it is of order n, then it is strictly greater than n minus 1. So graph G has tree width of n cross n grid is at least n minus 1, right. You can also work hard and show actually tree width of n times n grid is actually equal to n, right. So what does it imply? Okay, excellent. So clique cannot be an, clique as a minor cannot be a right obstruction for tree width, right? Because grid seems to be a form an obstruction. So if I can tell you that my graph does not contain some grid as a minor, does it imply tree width is small or big? Can I say this? Is it the real obstruction or not obstruction? And that is what we'll talk.